The first thing to take notice of is this idea of disjoint events. So you can write this definition down. Now this says events that have no outcomes in common or that can't occur at the same time. So in real life, anybody think of disjoint events?
Events that have no outcomes in common or can't occur at the same time.
Two different ways of looking at the same thing.
Can you give us an example and then maybe we can go on to it?
Yeah, I'll give you a real easy one. We're flipping a coin. How many events are possible? Can they occur at the same time?
No.
Disjoint events. Heads and tails are disjoint. They can't occur at the same time.
Like rolling the dice?
Ma'am?
Like rolling the dice?
Rolling dice. If I roll one die, can I get a 1 and a 5 at the same time? Nope, so those are disjoint. Historically in our country, is being a woman and being president, are they disjoint up to now in our history? Yeah. It won't always be so, but historically in our country, that's what it's been. If you were a woman, you were not going to be president. Those were disjoint events. Okay, any others? Can I be sitting here enjoying class with y'all and at the same time being in Weatherford walking my dogs?
No.
Disjoint events.
Only if you have a clone.
But I don't, alas.
Like madly.
Yeah, I don't. Another word for disjoint is mutually exclusive. If you have one, you can't have the other. Mutually exclusive. Having one excludes the other. You tell a little kid, you can have a Tootsie Roll or a Snickers bar, but you can't have both. Those are mutually exclusive. Those are disjoint events. And we're going to be using these things a lot. Venn diagrams.
Ew.
Not you.
Yes.
These illustrate a lot. These are going to help you. Now notice something. The rectangle here is the sample space. So everything in the rectangle is a sample space, and there's my S down there. How many events do I have? 2. Are they disjoint? Yes. There's no overlap. They don't share anything. There's no outcomes in common, if you will. Now, we don't know what's in those two things, but I can look at that Venn diagram and tell you right away, that's a Venn diagram of disjoint events. Without even knowing what's in them. We good?
Yeah.
Write this down, please. Now, yesterday, we talked about the first 2 rules. What were they? They're on that sheet I gave you.
Wait, ask the question again.
Rule number 1 was what?
Oh wait, I have that here. For any probability,
It has to be less than.
the probability is greater than or equal to 0 and less than or equal to 1.
Exactly right. So for any event, the probability is either going to be 0 all the way up to 1. It can't be less than 0. It can't be more than 1. That's rule number 1. Rule number 2.
Sum of probabilities is
Here's a sample space.
It's 1.
If this had a bunch of events in here, if I add up all their probabilities, I'm going to get 1.
Yep.
That's rule number 2. And now we get to rule number 3. This one. And it has 2 versions. This is version 1. And this says if A and B are disjoint, then I can use this rule, this version. This is rule 3, called the addition rule. And it comes in anytime you see the word or. When you see the word or, think this rule. For instance, I've got one die here, and I'm going to roll it once. I want to know the probability of getting a 2 or a 5. First question is, are they disjoint? Yeah. How come, Bryson? Elijah?
Because you can't have them at the same time.
Right. I can't roll a 2 and a 5 at the same time. They are disjoint. So I can use this version of the rule. So it's going to be probability of 2 plus the probability of 5. Well, the probability of 2 is what? 1/6. Same for 5. So I'm getting 2/6.
Yeah.
How's it going?
Good.
Like your shirt.
Thank you.
Right? So a third of, now what's this saying? A third of the time, if I roll that one die thousands and thousands and thousands of times, a third of the time I'm going to get a 2 or a 5. That's all it's saying. If I rolled it thousands of times and I only get it 2 or 5 one time out of 100, I'm going to think something's wrong with that die. Right? Just based on logic. Okay, odd or even? Are they disjoint? That's the first question you ask.
Yes.
Yeah, so I can use this rule. Probability of odd plus the probability of even what's the probability of getting odd?
3 out of 6.
So half. Even, same way.
Oh my gosh, you're doing
What's that saying? If I roll a die, I'm going to get odd or even every time.
Are there any imaginary numbers on that die?
No. This is not algebra. All the numbers are going to be right there.
Imagine if they made dice with like imaginary numbers.
So then I could say, well, I got a 7. You could go, no, you didn't. I go, well, yeah, it's imaginary. I got it. All right, so
Yeah.
odd
Oh,
or,
imaginary, you just make up your own number.
odd or 2. I'm just going to keep going like I have some sense of control here. Are they disjoint? Yeah. So the probability of odd plus the probability of 2.
I have a question.
Sure.
So like on example 1, it doesn't equal 1, but I thought they were supposed to equal 1.
If I added up all the probabilities.
Okay.
Okay, good question. All the probabilities in the sample space.
Okay.
We're just picking 2 of them out of there. Look at what, to go a little further on what you just said. If getting a 2 or 5, the probability is 2 out of 6, what's the probability of not getting a 2 or 5? 4 out of 6. Good question. Okay, probability of odd, we said was a half, so I'm going to write that 3/6. Probability of a 2, 1/6. So 2/3 of the time, if I do this over and over and over again, I'm going to get either an odd number or a 2. That's all it's saying. Probability is always about what's going to happen in the future. Stop right there. Anybody have a question?
Not the dice.
The dice. I'm going to roll them. 5 or 7. Are they disjoint? That's the first question you ask with these OR problems.
Yes.
Yes, they are. So I can just say the probability of 5 plus the probability of 7. Well, how about 5? It helps have this little guy. So 5, I can get, starting with this first column. 1, 2, 3. There's 4 ways of getting a 5. Out of how many? How many in all? What's our sample space? 36, thank you. So 4 out of 36. A 7, they're the ones in red. Six out of 36. So 10 out of 36. And if you want to reduce that to 5/18, you can. On a test, I'd take 10 out of 36. That's a perfectly good number. Please don't change it to a decimal, because then it gets nasty. Because of round-off error and stuff. Just leave it as a fraction. Fractions are your friends. Okay, how about a 2 or a 12? When you see that word or, think addition rule. Are they mutually exclusive? Yeah. So the probability of 2 plus the probability of 12. Well, how many ways can I get a 2? Just one, up there in the top left corner. So 1 out of 36. How many ways can I get a 12? 1, thank you. So 2 out of 36. Again, what are we saying? If I roll those 2 dice thousands and thousands and thousands of times, 1/18 of the time, I'm going to get either a 2 or a 12. That's all it's saying. The law of large numbers. Oh, look, I can do this. I can chain them along. Are 2, 12, and 11 all disjoint? Yeah. So I can just add up their probabilities. So 2, I know that was 1 out of 36. 12, same deal. How about 11? How many ways can I get an 11? Hmm? 2? Thank you, ma'am. So 4 out of 36. Again, if I repeated this a bunch, about a ninth of the time, I'd get a 2 or a 12 or an 11. And that works great because they're disjoint. How about 10 or a number less than 6? Are they disjoint? Yeah. I can't get a 10 and have it be less than 6 at the same time. So disjoint. So how many ways can I get 10? There's one. There's one. There's one. Is that it?
Yep.
So 3 out of 36. How many ways can I get a number less than 6? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice there's no overlap there. The drawing even shows you that. So I've got 13 out of 36 is my probability. Now you might be thinking, where does all this probability stuff come in? And it's going to really hit in the second half of our class, because then we're talking about stuff like, all right, this thing really did happen. How likely was it? And we're going to have to know the rules of probability to figure that out a lot of times. This comes up all the time in legal stuff. Somebody, if you're a lawyer, somebody might come in and say, I think I was discriminated against. I work for this huge company. They were going to promote a bunch of people, and they didn't promote anybody over 40. None out of 100 people. How likely is that to happen? Just by chance. Because you can't discriminate against people over 40. That's the law. People get around that, but you're not supposed to. So now what would we do? We would say, well, how many people at the company are over 40? What's the likelihood that none of them got picked? And then you go to court over that. And so imagine a jury sitting there, and you've got an expert witness that's a statistician trying to explain this stuff to a group of just ordinary folks that have never had stats. Good luck. It can get really weird. Let's keep going. A Venn diagram. If you'll write this down, we'll talk about it. Okay, so I'm looking at this. I'm saying, well, probability of A or B. I know it's an addition rule. So what's the probability of A? How many things are in A?
4, 6.
6? Here's A. Right, 6 things? Okay, so I've got 6 out of how many? No? How many things in the sample space? 10. 7 and 5 aren't in A or B, but they're in the sample space. Remember, we got to say, well, how many ways can I get something in A out of the total ways? There's 10 total ways. Venn diagrams can really help you. I'm not getting paid by the Venn company, so I'm just telling you, they can help you. So probability A would be what? I wrote it in the wrong place, didn't I? Six out of 10? How about B? How many things in B? 4. Here's B. So 4 out of 10. And so the probability of A or B, I'm just going, oh, that's an addition thing, so I add them together and I get 10 out of 10, which is 1, which says if I draw something out of the sample space thousands of times, every single time, that 1 says every single time, I'm either going to get something in A or B. Is that true? No. Sometimes I'm going to get a 7. Sometimes I'm going to get a 5. They're not in either A or B. What went wrong? Are A and B disjoint events? I cannot use that other rule. I've got to use version 2. On an OR thing, the first thing you ask yourself is, are these events disjoint? If they are, use version 1. If they're not, as in this case, you can't use version 1 because you get a result that's not right. So look what just happened. For A, I counted these 6 things right there, right? 3, 8, 2, 6, 10, 9. For B, I counted those 4 things. 1, 4, 6, 2. We counted the 2 and the 6 twice. That's what threw us off. So look what this rule says. Version 2 says, yeah, go ahead and add up the probability of A and the probability of B, but you counted that overlap twice. So we're going to subtract 1 overlap. We don't want it in there twice. We just want it in there once. So going back to this rule then, version 2, it's going to be the probability of A, which is what? We said 6 out of 10. Plus the probability of B, 4 out of 10, minus the probability of the overlap. So 2 out of 10. So now I'm getting 8 out of 10. And that makes more sense. Look at the diagram. If I reach in there and draw out a number thousands of times, 80% of the time I'm going to get something in A or B. The other 20% of the time I'm going to get either the 5 or the 7. So the math matches the picture in this case. You might also see the OR written like it is right down here, with a union in between. In math, OR also means union. So for those of you that did pre-cal, you know, a lot of times we did an interval that said, oh, this went from negative infinity to 3, and then union, something like 4 to positive infinity, something like that, when we're talking about domains. If you didn't have pre-cal, don't worry about it. But that union symbol also means OR. And if you think about the interval, it means either from negative infinity to 3 or from 4 to positive infinity. Those two things are disjoint. They can't occur at the same time. Stop right there. This is called the general addition rule, which means I can use it anytime. I can even use it with those disjoint ones. How? Well, if two events are disjoint, how much overlap is there out here? None. That goes away. That probability of A and B goes away because there is no A and B. There's no overlap. So that becomes version 1 of the addition rule. Right? If there's no overlap, this last part out here doesn't exist. So it just is 0. All right. I've got a regular deck of cards. I'm going to draw one card out. I want the probability of a king or a heart. Now, in a regular deck of cards, what do we got? We got hearts, diamonds, keep this color-coded here, spades, clubs. And in each one of those, there's 13 cards. So there's 52 in a deck. So, are king and heart disjoint?
No.
Nope. So I got to use the general rule. So I say, okay, probability, I can do better. Probability of king plus probability of heart minus the probability of both. Probability of a king, I've got 4 kings out of 52, so that's 4 52s. Hearts, how many? 13. Both, how many things are a king and a heart? So I've got to subtract that. There's my overlap. So I've got 17 minus 1, so 16. And there's my probability. You can reduce it. What would that be, 4/13? You can leave it like that. On a test, I'd just assume you leave it like that. What's that say? If I repeatedly drew a card out of a deck, looked at it, put it back in, shuffled again, 16 out of 52 times, I'm either going to get a king or a heart. Okay, let's try a couple more here. Face card or a spade. Are they mutually exclusive? Face cards are Jack, Queen, and King. Are they disjoint?
No. Oh, wait, no.
Because I could have Jack of Spades, right? Or Queen of Spades. Okay, so they're not disjoint, so I've got to say the probability of face card plus the probability of spade minus the probability of both. Okay, face card. I've got 3 in each suit, Jack, Queen, King, so I've got 12. Spades, 13. And again, I'm putting this over 52 because that's how many things are in our sample space in a deck of cards. Minus, how many are both a face card and a spade? 3, okay. So I've got 25, take away 3. There's my probability. Leave it as a fraction. Do we need to talk about this? Keep going. Even or a diamond, are they mutually exclusive? Okay, so the even cards would be 2, 4, 6, 8, 10. They're not disjoint. So probability of even plus the probability of diamond minus the probability of both. Okay, even cards. So 2, 4, 6, 8, 10. That's in one suit. So 20 of them, ma'am?
Is a queen technically even?
No, face cards aren't either. So 2, 4, 6, 8, 10. That's in one suit. So 5 of them in one suit. We've got 4 suits. So 20. Diamonds. 13 out of 52. A fourth of them. How many diamonds are also even? Because we counted the, yeah, thank you, sir. So 5 out of 52. We counted them once with the even ones, right? So I've got 33 minus 5, so 28 out of 52. Last one on this page. Red or ace? Mutually exclusive? No. So probability of red plus the probability of an ace minus the probability of both. Okay, red. Thank you. 26 out of 52. Half of them are red. Plus, how many aces? Got it. 52 minus, how many are both ace and red? 2. So I've got 28 out of 52. Now notice these two probabilities are the same. So if on a quiz it said, which is more likely, drawing an even or a diamond, or a red or an ace? The answer would be they're the same. Let's keep going. Now sometimes, don't copy this down. You can take a picture of it here in a minute. But sometimes this comes in a table. These probability questions come in a table called a contingency table. Meaning you can look at this in a whole bunch of different ways. If you're lucky, they've totaled these things up for you. If you're not so lucky, you get to total them up. So you got to total each column and each row. Okay? All right, so probability of male. Well, I'm going to look at this row right here. So what's that? In the sample space, there's 2,200 people. I'm sorry, 2,200 choices. No, it is people, because these, yeah. So 2,200 people. How do I know that? Because it's right down here. So what's the probability that I reach into this sample space and I pull out a name and it's male? How many males are in this sample space? Good. 1,200 out of 2,200. And so I can just real quick do that. So 12 out of 22. So the probability of reaching in and drawing out a male's name, just completely random, is 12 22s. Okay. No addition rule at all there. Okay, how about pulling out either a female name or somebody that likes a cone? Are those mutually exclusive? No, because some females like cones. So I've got to do the general addition rule. So the probability of female is what? It's going to be probability of female plus the probability of people like cones minus the probability of both. Okay, female. How many?
1,000 out of 2,200.
Good, so 1,000 out of 2,200. How many like cones? Good. 635 out of 2,200. How many like, she's getting that from right here. How many like both? How many are female that like cones, in other words? 335 out of 2,200. So what would you do? You'd say, well, 1,000 plus 635, take away 335, put that number over 2,200, you got it.
Will we ever, for whatever reason, get a different denominator?
Yeah, that's coming up in section 5.4. And this is a little bit of foreshadowing. In 5.4, you'll get questions like, given that you drew a female name out, now what's the probability she liked a cone? That changes everything. Because now you're not talking about the whole sample space. You're just talking about the sample space of females. Yep. How about, let's skip that one for a second. Not Sundays. Okay, we'll come back to that. Male or somebody likes a cup, besides my bulldog. Male, we already know, was 1,200 out of 2,200 from the first question. How about cup? $1,002 out of 2,200. How many males like cups?
592.
Right? See, these tables make this kind of thing a lot easier. So you just add up 1,200 and 1,002 and then subtract 592 and put all that over 2,200. Let's look at the last rule real quick. Rule number 4, if you'll write this down. This one's going to come in handy. A complement with an E in the middle there means either something that completes something or is the opposite of something. Okay, now let's talk about that in context. In geometry, if I have complementary angles, what does that mean? Anybody remember? Complementary with an E in the middle like this. It means if you add them together, you get 90 degrees. So you could say, if I've got a 30-degree angle, what's its complement? In other words, how do I take that and complete all the way to 90? Well, that's 60. What are complementary colors? Any artists in here? Opposite on the color wheel. So it's got a couple of different meanings. Here it just means that rule right there. If I want the probability of, well, let's say on a die, what if I want the probability of not getting a 4? Or look down here at this one at the bottom. Probability of not getting a 6. I could say, well, that's the same as 1 minus the probability of actually getting a 6. Which is what? 5, 6? Now, on that one, I could just say, well, there's 5 other sides of 5, 6. But some are not going to be that obvious. And this rule is going to save your hide sometimes. It just says if you want the probability of not something, it's the same as 1 minus the probability of whatever that something was. How about not a face card? What's the probability of a face card?
12 out of 52.
Mm-hmm. So 1 minus 12 out of 52. So what is that, 40 out of 52? I don't have to count up all those other things. So let's go back to this one. The probability of not a Sunday. Well, Sundays is 384 right here. So 1 minus 384 over 2,200, whatever that comes out to be. That's a fast way of getting it. This complement rule is going to save you some time sometimes. And sometimes it's the only way to work something. You'll see as we get further into this. So I've got probability of E is what? There's 15 things in all. Three out of 15. Plus, what's the probability of F? Five out of 15. Probability of both. How many things in the overlap of E and F? One. All right, thank you. So that's going to be what, 7/15? Look at the second one, F or G. First question you ask is, are they disjoint? No. So it's going to be I got to do the general rule, so probability of F plus the probability of G minus the probability of both. F we decided was 5/15. G is 5/15. Both. 2. So 8/15 is the probability of getting, I reach in there and draw a number out. If I do that thousands of times, 8/15 of the time, I'm going to get something out of F or G. How about E or G or H? Disjoint or not?
But H is disjoint.
Or disjoint.
E, G, H. Is there any overlap in any of those? No. So I can just...
In the future though,
Hmm?
like make E and F overlap, but not H.
H is out there by itself.
No, I know, but like, will they ask the question?
Could. They sure could. That's why I didn't ask it that way. So E, we got 3/15. Plus G is 5/15. Plus H is 2/15. So 10/15. So if I did this thousands of times and drew something out of that sample space, 2/3 of the time I'm going to get something in E or G or H. How about not G? Here's the complement rule. So 2/3 of the time I'm going to get something that's not in G. E or H, well, we already decided those are disjoint, so we just add them up. So I get 3/15 plus 2/15. So 1/3 of the time, I'm going to get something that's in either E or H. Okay, slightly different twist here. The reason I put this in here is because the homework has some questions like this. So let's map out what they gave us. I'm looking at this. I've got the probability of M, the probability of K. They want me to find the probability of M or K, and they're giving me this out here, which indicates what? The overlap. When it says M and K. So, how do I find this? This equals the probability of M plus the probability of K minus the probability of both. M and K's, in other words. So, I'm getting, what, 0.2? 0.35 minus 0.1 equals 0.45. One to go. I'm just looking at it. I've got probability of A, probability of, they're giving me the probability of A or B, and the probability of A and B. Well, seeing this out here tells me general rule, right? Because there's an overlap. So I'm looking for the probability of B. So if I take the general rule and say, okay, probability of A or B equals probability of A, probability of B minus the probability of A and B. So let's fill in what we know. A or B we know is 0.035. So that just got that one. Probability of A is 0.4. Probability of B we're looking for minus probability of both. Now what? Back to algebra. So I got 0.4 minus 0.2. And so probability of B is going to be what? 0.15. So they can twist these things around. And I just wanted to show you these because this kind of stuff is going to be in the homework. That's it for me, y'all.